Hello everyone, good afternoon. Welcome to my presentation. I'm Cindy Li and assistant professor at Arizona State University. Today I will give you a brief introduction about my research. The topic of today's talk is fabrication of biomimetic functional materials and structures by multi-scale nanocomposite printing. As we know, nature provides us many biological structures and smart material systems, and they inspired us for a lot of innovations in different areas. I would like to raise two examples. The first one is mosquito eyes inspired compound lens design for large field of view. And another good example is shark skin with pattern textures. So researchers are inspired by these structures and further created devices to reduce drag force. The performance modification using biological features is desired and sometimes is critical to achieve certain functionalities. So when we take a look at the biological material systems, we found several common features. They are all multi-scale, multi-material, and multifunction. All this actually raises a good question for us. How do we reproduce that kind of complex biological materials and structures for some real application in our daily life? Actually, additive manufacturing is a potential answer for us. So over the past 30 years, the manufacturing community has been benefiting a lot from additive manufacturing. So thanks to its capability of fabricating complex geometry from its 3D digital model. The principle of additive manufacturing is quite straightforward. So after we get the 3D model, we slice it into a set of 2D layers, and then we accumulated the material layer by layer. Recently, a lot of effort has been made to develop new additive manufacturing process to fabricate different type of kind of material. And additive manufacturing process has widely been used in applications such as biomedical engineering, automobile, aerospace, electronics, and sustainable energy. The revolution of additive manufacturing has brought us many opportunities in producing bio-inspired material and structures. So we have a review paper worked on the recent progress in biomimetic additive manufacturing. Based on the 3D printed bio-inspired material and structures, a lot of interesting applications have been developed in each field, such as optics, shape changing, electronics, mechanics, fluidics. They successfully use different additive manufacturing and processes and achieve the bio-inspired structures. However, there are still some common issues and challenges in this field. So it's hard to fabricate multi-material, multi-scale structures. So our lab of manufacturing innovations actually is developed and utilized the novel additive manufacturing process to create bio-inspired functional devices and to address some real-world challenge in the field of bio-inspired design and manufacturing. So here is the link of our lab website. Please feel free to visit our website. Uh, the research of our lab is focused on develop a novel advanced manufacturing process with integration of bio-inspired design methodology and functional programmable material to achieve the development of multifunctional devices with multi-material and multi-scale structures for different applications. The material we use is more related to nanocomposite, bioceramic, and programmable polymer. So we did a lot of work based on the Bell-inspired design and manufacturing. So the applications cover the biomedical, interfacial, and sustainable energy. Due to the time limitation, I just give you several examples of our research work. The first one is the Solvina Monasta leaf-inspired multi-scale droplet gripper. So as we know, the robotic arms is used to grab the rigid object. Actually, it's hard to use to grab the liquid. So how to solve this problem? To we get the inspiration from the nature. We found that there is one plant called Solvania molasta. So they have a special egg beater shaped structure. And it can grab the water droplet, but it shows superhydrophobic property, unlike the lotus leaf. So when we take a look at this structure, so the total height is around 2 millimeter, but the hair, the diameter is only 13 micron, and they has very unique hydrophilic nano tips to grab the water. So we developed our immersed surface accumulation printing process to reproduce such kind of structures. So we add the carbon nanotube, and we found we can print such kind of superhydrophobic structure, but it can grab the water due to the nanoscale hydrophilic carbon nanotubes. Based on these printed structures, we can do the liquid separation, the water oil separation, and also we can remove the oil from the liquid. Now there is another research in our lab. It's related to the cactus-inspired multi-scale structure for water harvesting. So we know that the cactus can live in harsh environment, especially in Arizona, where in the desert. And the cactus can survive because it have the unique multi-branched spines, so it can collect the water due to the special very sharp tip. And we get the inspiration, so we use our immersed surface accumulation approach to successfully reproduce that kind of multi-branched structures using nanocomposite. And we optimized the arrangement of multi-branched structures, and also we studied the design for different the shape of the artificial spines. And finally, we can fabricate the bio-inspired surface with artificial spines to collect the water from the environment. So here is one video, so it can gradually collect the water droplet from the outer environment. So another example of our research is focused on the lymphatics-inspired microneedles for painless drug delivery. So the microneedle actually have a lot of advantages over the traditional the injection needle, and the microneedle has widely used in different fields. However, for the current microneedle, due to the limited mechanical property, the patient will feel the pain when it inserts. So we get the inspiration from the lymphatics, which prove the highest material in the nature. So when we take a look at their architecture, this is because it has the magnetic responsible mineral fibers inside the polymer matrix. Based on that, we developed our magnetic field assisted 3D printing approach. then we can align the magnetic responsible particles inside the polymer matrix. And the 3D printed microneedle exhibit very strong mechanical performance. So when we insert it in on the surface of mouse, it cannot feel any pain, and also it can wear in a long term. The last one I would like to share to everyone is a hair-inspired flexible liquid sensor. For the human hair, it have a unique property. It can absorb the water, and after absorb the water, it will swallow and have the shape changing. And based on that, we developed a nanocomposite mix with the hydrogel and the carbon nanotube. So when it swallows the water, the shape will change. The gap between the carbon nanotube increase so that the resistance of the printed material will be increased. Based on this principle, we developed the liquid sensor with the capability of detecting the position and the direction of liquid leakage. And this liquid sensor shows a remarkable high sensitivity and a quicker response. It opens the perspective for design 3D printed sensor with special distribution of material to achieve anisotropic sensing properties. So the last one I would share to everyone is we have a special issue on the topic of design and manufacturing of bio-inspired material and structures. So here is the link of our special issue. Welcome everyone to submit the papers. So at the end, I do believe the innovation of manufacturing will eventually lead to the revolution of industry. And welcome everyone to have the collaborations with our lab. And I would like to say thanks to my funding agency. And also thank you everyone for attending my presentation, and have a nice holiday season. Thank you.